This project coordinates the action of 20 partners. 10 of them are laboratories for nanoscience co-located with large-scale facilities, synchrotrons at different places in Europe, and a neutron source in Munich. And these have some adequate capacity to sustain a user program, and this is what is supported by the Horizon 2020 NFFA-EUROPE project. With this 4-year project, we plan to establish a strong connection with the user community to demonstrate the power of our concept of bringing together nanofoundries and fine analysis laboratories to prepare for a follow-up that may imply establishment of more permanent research infrastructure. NFFA is about integration, so the offer to the users is articulated in access to lithography and nano-patterning facilities, to growth and synthesis of nanostructure facilities, to characterization tools spanning from clean room methods all the way to neutron scattering and synchrotron radiation spectroscopies, and of course to theory, where advanced codes would allow users to submit theoretical projects and to have access to high-power computing.
Fabrication of nanostructures and patterning of surfaces are currently adopted in a vast range of high-tech industrial applications. For example, in production of computer chips and memory devices. And the application area is rapidly extending to new fields. We provide access to state-of-the-art tools at several institutes across Europe, and, for example, e-beam lithography and photolithography. In the framework of NFFA, we also provide expertise in these methods, in particular to achieve nanostructures with very high resolution or to realize highly sophisticated devices.
Growing high-quality nanomaterials is the starting point of any experimental research in nanoscience. Here you will find powerful tools to prepare artificial materials with a tight control of atomic structure and shape. You can prepare thin films, multi-layered materials, nanoparticles, nanowires, nanodots, and so on. The facility offers vapor deposition techniques and different chemical approaches adapted to many sorts and compositions of materials such as oxides, semiconductors, organic, hybrid, and even biological materials. These nanomaterials may have a myriad of novel properties and enhanced performance in practical devices. They can have huge interest in electronics, in spintronics, photonics, sensors, in energy applications as solar cells, energy storage, electricity transmission, and in biomedical or pharmaceutical uses, such as drug delivery and biomaterials.
The Theory and Simulation Group offers computational support to experimental NFFA users. We provide scientific competences, state-of-the-art software, and high-performance computational facilities for modeling materials at the atomic and molecular scale. The main computational methods are based on density functional and many-body perturbation theories. These allow for the precise simulation of a wide range of materials properties, both in the ground and in the excited states. Our simulation will assist and guide the interpretation of complex spectroscopy and microscopy data, and beside this, we aim at identifying useful guidelines for the design, growth, and synthesis of novel functional materials.
So the characterization offer will provide all the tools necessary to characterize the fabricated sample, and it goes from the intimate atomic structure to the macroscopic physical properties. We have divided this characterization offer into 3 installations. The first one is dedicated to unveil the atomic structure and morphology. This includes far-field and near-field microscopy, and also structural characterization in large-scale facilities through X-rays and neutron diffraction. The second installation aims to give access to the electronic band structures and the chemical states. So it includes photoemission and spectroscopy in a wide range of wavelengths, from X-rays to far infrared radiation. And again, we are dealing with standard laboratory equipment together with spectroscopy at synchronous facilities. And finally, the third installation concerns characterization, leading to the macroscopic electrical, optical and magnetic properties.
So an initiative like the NFFA is a very interesting initiative from a user point of view, like myself, because then you basically can access various facilities across Europe to get equipment that your own group might not have, and you can basically initiate collaborations across Europe. And that as a concept is a very interesting, both for the equipment potential within Europe, also then looking beyond the equipment is also a question of the human potential. So it's really adding to the strength of Europe as a place to do research.
European infrastructures and researchers have a huge amount to offer to industry, but they're more often than not severely underexploited for industrial innovation. The challenge is simply that industry doesn't know what is available, how to access it and how to combine the different offers. NFFA now combines a wide range of European research infrastructures with access to their expertise and skills for industry into a seamless package. Industry can apply for beam time, access to the facilities and get it for free, but with the obligation to publish, or can come and buy the access for their own proprietary confidential research.
The properties of engineered objects, from technical textiles to sport goods or tires, just to name a few, depend on the properties of constitutive materials from the macro scale down to the nanoscale. And while engineering at the macro scale is a standard, is what we do every day, engineering at the nanoscale is still in its infancy. NFFA-EUROPE offers, in my view, a tool to investigate and possibly better control materials at the nanoscale, which is fundamental to improve current products and create new ones.
The ensemble of the data produced under NFFA will constitute the basis for an advanced data repository for nanoscience with an advanced data management system that will define the metadata standard for nanoscience.